Okay, I guess they will join as we go. We have here a room of people. I don't want to move my laptop because there is a lot of cables around, but there's students here, John, waving. And then on this side, and there is I'm in the middle of the classroom, so whenever other parties join in, I guess they can just carry on. And this is recorded, so they can watch the recorded version. But let me just start by saying thank you so much for your time. We're so excited to hear your talk. These people here are so hungry for technology and where the West is going with technology. So we wanted to put this event together for them. There are a lot of young entrepreneurs, and they've worked on a variety of technology, and they're really interested on hearing about distinguished engineers from you and from the States on these topics that we have put up forth in there. So this is the Washington Education in Kosovo Center in Pristina. When the other two parties join, we might just hand over to them for 1 minute introduction. But I guess we can carry on, so I'll just pass it on to you, John, and I'll let you introduce yourself and move on with the rest of the slides that you have. You can share your screen. Up left corner, there's a green button. If you don't see that, I can share, I guess. And
no, I've seen it.
Okay.
So I'll start off. So my name is John Hatch. I've been working in embedded technology, and now I work on servers for probably 20 plus years. I worked originally in the operating side. I worked on compilers, debuggers, Visual Studio, the runtime, and so I've had a lot of experience with like the entire infrastructure on how you go from writing code to actually making it run on a device. When I first started, you know, this was like a very typical device, was just a simple little black and white, you know, I mean, maybe this was running like an ARM7 or something like that, no virtual memory. And then over the years, I mean, actually, this was the device when I first started. It's much bigger. Then it got smaller, and then eventually we started seeing screens were getting a little more sophisticated, color screens. Eventually started connecting, being able to do little miniature browsing and stuff. And during that time, too, was the world of Palm Pilots, which quickly went obsolete, but was pretty spiffy when it first started. And then this was a prototype from Phyllis. This was running MIPS processor. This was at the beginning of Windows CE, which was in the early mid-90s. So that's when there was a huge competition between MIPS, ARMs, PowerPCs about what type of device would work. Here's an early prototype. Some of these early prototypes, basically the batteries would last about 2 hours. I think on one of these devices, the batteries would last 2 hours, whether if you turned it on or not. Black and white screen. The company I used to work for, we developed this machine, which was very spiffy. Now we're starting to see virtual memory, color screens, internet connectivity, but very slow speeds, very limited memory. Hewlett-Packard came out with this device. This was actually a pretty nice device, and it sold well, but again, nobody would even consider using one of these anymore. And finally, the explosion. You know, nowadays we have this is an old iPhone, my new Windows phone, and one of the themes is as the devices explode, so does the computational power and what people can do with it. And so let's just go ahead and jump into the deck now. Hang on a second. This one. No. Desktop. So are you seeing my desktop?
Yeah, just don't hit the play button because we won't see the slides. So you'll have to switch the slides, I guess, from PowerPoint itself.
Okay, so you see that?
Oh, we see this. Okay, let's move.
So what I'm going to do is I'm going to focus on talking about how operating systems is part of this world and sort of the benefits about studying operating systems. First, let's start with kind of the trends, some of the major trends that are affecting the world, and then we'll talk about like operating systems specifically. So probably, this one's pretty obvious. So back in the 70s, you had mainframes. There were roomfuls of machines requiring squads of people just to maintain them. But these machines were actually very limited, probably less than a megabyte of memory. You had, the hard drives were the size of cabinets, and if they held 5K, you thought you were great. And then slowly, towards the end of the beginning of the 80s, you started seeing the introduction of PCs and motherboards, but still the original cost, the cost and power was pretty limited. And then, then at the beginning of the 90s, and definitely, throughout the 2000s, you're getting this idea of what's called a system on a chip, where instead of having a motherboard that has all these peripherals on it, and you have just basically a dedicated CPU in the middle, and then the peripherals as individual components, the trend is to build these type of devices. I mean the iPhones of the world, the manufacturers are starting to integrate all those peripherals into a single chip. And so they call that a system on a chip, and that has a lot of benefits. One, it means the costs are dropping, because every time you have a separate component and you need to solder it to a board, you're introducing costs and errors and the chance that the device is going to fail. And so the manufacturers, what they really want to do is put the entire computer on a single chip and only have the connections that are minimally required, such as basically to the radio, to the screen, and to the touch sensors. Anyway, this is creating a world that we could call now you're starting to see a world of interconnected devices, internet connected devices. Is a pretty big explosion. I mean, now you have an explosion of cheap devices, and so right here, so in the picture, it's mostly personal devices, but you're also seeing throughout industry where now, for example, we're starting to connect. In the commercial world, you're starting to see almost all kinds of devices. For example, there's in Washington right now, the house power meter that measures the power meter now is Wi-Fi connected, so that to measure your, to basically figure out how much current you're using, all they have to do is drive by your house, and the truck will connect to your house, figure out your usage, and then move on to the next house. And so all those, you're starting to create this world where almost everything is connected. And a lot of it is because, and then not only do you have the devices, the prices drop so much that you can start building all these devices and spreading them out in the world, but the fact that they're internet connected means that the device is even more powerful than it appears, because now you're leveraging the power of servers and cloud storage, so that, in other words, the device, if it needs to do something computationally intensive, it can just simply make a request of a server, and the server will grind through the problem and then return the answer to the device. So you can have very powerful devices. And what they're connecting to is these huge global data centers. Global data centers are starting to spread all over the world. So this is a huge Microsoft data center in San Antonio. And if you look carefully, you can see the cars down in the corner. So give you an idea of the scale of the machine. And these are, I know it's like, for example, I work for Microsoft, so I know that that we have this one in San Antonio, just about 2 hours east of where I'm at here in Seattle. We have one. There's a town called Quincy, and it has 6 of these. 3 of them belong to Microsoft, and 3 others belong to other companies. And it's a little tiny, sleepy town, but it has the cheapest electricity in the United States, so that's why it's really popular for building data centers. These things require massive amounts of electricity to run. And inside them, now you see, I mean, it's rows and rows and rows and rows of, it's like walking to this, like the biggest library you've ever been, and it's just racks and racks and racks and racks of servers. It's quite impressive. I did an all-day tour, and they took us through all the entire systems. And so each one of these racks has basically, it's a collection of servers. So, if you look on the right side of the screen, a server, is this flat computer. Basically, the one at the top right, you can see from the cooling fins that it has 4 processors. So those
So your
processors. Wait, excuse me.
so your team works on this data center, John? Just to
Yes.
clarify.
So my team, we work. Our software runs in these data centers. We basically we build. Instead of having a single server running a single application, what we actually have is a collection of servers. Our application probably uses at least 20 servers that are interconnecting with each other. And that's the thing is, having so much computing power really changes the way you can solve problems. You can start doing things like you dedicate an entire computer just to run one single application. So that way you can guarantee that that application is running because you can have other computers checking to see if that computer is still alive. And then you can have standby copies waiting. And so if anything goes wrong, you can easily switch to a new server. And so now you have this web of servers connecting to servers. So all the project I work on requires that we maintain a lot of data and that we maintain the integrity of the data. So while we run primarily in Quincy, which is east of here, in the background we're constantly copying all our data across the country to West Virginia, where they have another big data center. So not only do you have all this computing power, but you also have layers and layers of redundancy to keep it all alive. So so if you lose a data center, that you can continue operating and continue on keeping all that data alive. One of the things that was interesting when I was at the data center was we walked by this huge rack of computers, and they said that's Bing, so we just had this, gosh, how many? There's probably several thousand servers all in a row off to one side, and that was basically serving up Bing. And that was only one copy of Bing. So there were multiple copies of the Bing system all across the world. And one of the things about the servers is that you want to build data centers close to where people live so that you can reduce the latency. And so when people make requests, the closest data center serves it. So if I do a search on Bing, my search results are coming from Quincy. If you do a search result, if you go to Bing and do a search result, your search results are probably either coming from Germany or Dublin.
So
Because and I know that we're building more and more data centers throughout Europe, so that the idea is that any data center is at least 50 milliseconds away from, so any request only takes at most 50 milliseconds to be answered. And a lot of that's the physical limit of how fast electricity travels in the wires. It's pretty interesting that you would, that you have so much computational power that the physical limits come into play, and so you start building computer centers that are, where you build them has a lot to do with the speed of electricity in the wires.
You don't mind asking me questions in between that?
So then when you have servers come in different sizes, and so we spec out, how much storage we want versus how much computing power we want. And so we go through a process. We say, okay, we're going to build out a new system, and we'll spec out, and you say, well, we need four servers with this much storage. For example, we just built out a system where we bought eight servers. Each server had 48 terabytes of data of storage on it. And so then we could create a system where we put 4 of them in Quincy and 4 of them in West Virginia, so that we could constantly back up our data. And anytime we needed to, we could roll over from Quincy to West Virginia in case there was a problem with our Quincy servers.
John, let me know when we can ask a question real fast.
Sure.
Since you're talking about the data center, I know people here would like to know, what's the security level there, or the physical security? Are there security guards in there? Is there a process?
Oh, yes, it's actually layers of security guard. For one, you can only visit by invitation, and then not only do you check in, well, the first security is that the buildings are completely unlabeled. It's just a huge white building out in the middle of the field. And in Quincy, they also do a lot of apple farming, and they have these huge warehouses that look almost identical to big data centers. And so when you drive by, you might not even realize you're driving by a data center. Probably one one physical indication that you're close to a data center is the size of the power plant right beside it. So you'll see big transformers. You see huge power lines coming in, and they're stepping down because these things require huge amounts of current. It's not unusual for a rack of computers to take 2 kilowatts of energy, and so you're starting to talk about a data center taking megawatts. I think the one in Quincy, one building alone is 10 megawatts, and they have 3 buildings, so we're talking 30 megawatts of power just to keep all the computers alive.
So just to emphasize, internet was the one that pushed towards creating those data centers. Is that right? Or?
Yes, that's correct. So basically, so once you can connect a device once you connect a small device to the internet, now you want to be able to leverage that device and to be as powerful as you can. So you can either try to put all your costs into the device and make the device as powerful as you can, or simply make it powerful enough to display the screen and interact quickly with the user and have a good internet connection. And therefore, you can actually answer a lot of questions on the server. And so you can push off a lot of the computational power onto servers and leverage it. So for example, when you go onto your phone, and you use Siri or Cortana, and you ask a question, well, your voice is being synthesized. It's being is being sent over voice over IP to the data center. The data center is actually the one that's interpreting your voice, figuring out what it is you're requesting, running it through a huge natural language processor in order to understand what it is you've requested of it. And then once it's turned that into an understandable query, then it sends it to Bing, and Bing is like racks and racks of computers all racing simultaneously looking for the answers. And then so that's the thing. It's not when you ask a question of a search engine, you're not asking. It's not between you and a single server. It's between you and maybe 100 thousands of servers on the other side that are all racing to give you an answer. And that's how the answers are so quick. Each server is working on a little tiny piece of the problem, and then you have another server that aggregates all the answers and presents it back to you. And that's one of the ways that you can get this really fast interaction between a small device at the end and a big cloud server. So basically, the devices at the end, we call that the edge. So you have all these edge devices that are making requests all to a central location that's actually doing all the serious computational work. And kind of relating that back to Chris's talk, Xbox One is starting to do things where they're even leveraging the power of servers to help Xbox One. The obvious one is Xbox Live. You can see, Live is connecting you to all these different machines and stuff like that. But even more so, games are starting to get to the point where they want the high fidelity the high fidelity experience. And the way they're solving that is basically your Xbox One would make a request to a cloud of servers running graphical engines, and they would render it on real time. They would render really high definition images and scenes and send it back to the Xbox. And so now the Xbox is being able to display almost in real time really high fidelity worlds that are beyond the power of that one Xbox, and is being able to do that by leveraging the power of the servers. And so and that's a really powerful example of what's going on. So we're just now starting to reach the world, understand the capabilities that we can bring to the world by connecting these edge devices to these big computational centers, and being able to solve problems that and deliver services at a level that was unimaginable just even like 5 years ago. And then on top of that, so now we have like rooms and rooms full of servers, all running an operating system. But the people that are working with these servers have realized that we can even extend it even further by virtualizing the hardware. And what that means is that you run a specialized piece of software on your base operating system. For example, you run Hypervisor, which is sort of like an operating system for operating systems. And it is able to run, it basically creates these virtual copies of hardware, and then guest operating systems like like Windows or Linux or anything else can now run simultaneously on the same hardware. So there's cases where you might have a single piece of hardware and it's actually running 8 copies of operating systems on it. And each operating system it's running creates its own completely separate environment, so that there's no way, so you don't know if you're, so when you request we call them computational power, you request a compute, a compute power in a compute entity from a data center. You don't know if you're actually running alone on your hardware or you're running with multiple other copies. So lots of other people are using your hardware, are sharing the same hardware with you, and when you look at your software can't see that at all. You're completely isolated from one another, and this creates all kinds of wonderful things that they can do, because now we can turn these individual operating systems into images, which are basically a huge file that has everything in it: the operating system, your application, all your data, or anything like that. And if that server goes down, we can boot your image on another server, and you won't even know it. So we can easily transition from one server to we can change the hardware underneath you, and your application won't even realize that it's changed. And your environment's exactly the same. Everything's working exactly the same. So there's even another layer of power that's added to the data centers that's really incredible.
So at high level, virtualization is to leverage the computing power of more servers. Is that what we can say about virtualization?
Yeah, so it's to basically leverage the power of these servers. Are powerful enough that, for example, most websites are sitting around quietly waiting for somebody to make a request for them. And so that means that you're kind of wasting cycles. And in data centers, basically, once you turn on the server, you're already paying the cost for the power and the cooling to keep that server up and running. And so people who manage data centers want to maximize the amount of utility you get out of your server. And so they will run multiple operating systems on the same server in order to make sure that server is busy 24/7. So it's constantly working, because any wasted cycles we're just burning electricity.
Right.
And that way, too, so now the data center is even more powerful than just the number of servers in it, because now it's the instances of operating systems that are inside that data center. And so it's really all about being really cost-effective to use as much, to create as much computational power available to the world with, but using the least amount of resources. So electricity is expensive, the machines get hot. So you want to be able to maximize how much work you can do with that computer, and hardware virtualization is a huge trend towards doing that.
Got it.
Does that make sense?
Yeah. I'm gonna go in more details with the guys here on the technical part, but we love those images that you were showing us with the servers. So the audience might not be that technical in different locations, John. Just so you know.
Oh yeah. So I know. So I'm going to try to I'm trying to whet everybody's appetite, So even if you don't understand it right now, at least now you know that it's out there. I mean, this was pretty technical, and I was debating whether to put it in, but I thought it was pretty interesting, so I threw it in. So just to summarize, so now we have the trends, lower hardware costs. It's an explosion of computing devices, and all these devices are now powerful enough to have their own operating systems. And so on the lower side, you're basically starting to see devices everywhere. It's not uncommon for a modern car to have 32 CPUs in it. And then, so not only do you have your phone, but eventually you're starting to see devices all over the place. There's, for example, internet-connected thermostats, even light bulbs that you can control with applications from on your phone. So so now, with the cost of the processors dropping so much, it's not unusual to have a pretty sophisticated processor that has memory built into it, all the connectivity it needs, and to be able to run an operating system basically for under $1. And that's huge. That means
Wow.
that people are just adding computing power, well, to everything. And that's what we're going to see. Pretty soon we're going to see almost everything has a computing power. For example, there's even people that have invented door locks for your front house, for your front door, that can detect that you've walked up to your door and will unlock the door automatically for you. And so that's it. That's a lot of computing power simply to sit there and wait for you to open the door for you. And it would have been unheard of just a couple of years ago, but now it's so cheap. Why not? Let's do it.
Wow.
And then on
Yeah.
the high end, you have servers that are not only is it a sophisticated server with multiple processors. You might have 8 processors, and those processors now have multiple cores. So you might even have something like 8 processors and 4 cores inside each one, and each core can run 2 threads, and so it's like a single motherboard is the equivalent of 16 computers or 32 computers just from a few years ago. And so now you have all kinds of computational power, and now we rack them up inside these. We rack them up, and then we virtualize them so that now we can, now we can move images back and forth from them, and just basically create this environment of computational power, and stand up all these applications. And all these applications can now solve and serve up solutions to all these devices on the edge, and that's a really powerful. And so that's creating something, a new thing in the world, and the term is being called the Internet of Things. So
Yeah.
what we're seeing is an explosion of devices, and so people are estimating that in 10 years, by 2020, we're going to see 50 billion devices connected to the internet. I mean, that's a phenomenal number. I mean, it's just an explosion of devices. And those devices are all over the place. So here's kind of a good diagram of what I'm talking about. On one end you have the consumer. The consumer now has a house that's whose the sophistication is increasing. By leaps and bounds. The consumer now walks. So probably a number of you have smartphones. Your smartphone is considerably more powerful than a PC 10 years ago. But not only is the device more powerful, but it's connected to a data center, and so now it can serve up maps. It can serve up, it can answer questions. Basically, you just simply, I just talked to Cortana, and I say, what's the population of this city? Where's the nearest gas station? Where's this? And this huge data center can now answer my questions and render the data for me. And so then it's for the medical field, it's if you walk into a modern hospital, there's starting to be so many devices where they're starting to do things where you will walk in and they will attach a device to you, and that device will do nothing but monitor your health, and you'll be able to walk around the whole time in the hospital with it, and they will know exactly what your blood pressure is any time of the day. Computational for automotive, we're starting to see, for example, you may have heard of Google's self-driving car. Well, if you look into how that car works, the car is sophisticated and has a lot of computational power, but the real thing that makes it work is that it's connected to a data center, and the data center is doing all the calculations and helping it figure out where it is, what is it seeing, what should it do, how should it plan out its route. All that heavy lifting is actually being done back at the data center. And in industry, it's an explosion of industries. For example, I noticed earlier people were talking about Amazon. Well, Amazon's starting to build out their warehouses with tons of robots. And so the requests can come in, and the robots actually go out onto the floor and fetch the merchandise and bring it to the worker, and the worker just simply verifies that it's the right device, the right merchandise, puts it in a box, and off it goes. And all that's starting to be computerized with just swarms of robots running independently of one another, all going off and fetching devices and working 24 hours, 24/7. And of course, in industry, it's explosion. I think one of the interesting things I just recently read about internet-connected cows. So the cost is enough so that farmers can attach a device to every cow in their herd, and then he can sit back in his, back at home and know the health of all his cows. Exactly. Where they've been doing, have they been eating recently? And just collect all this data to help them, maintain the health of their animals at a lower, much lower cost. They're even starting to build. Excuse me.
My uncle would love that. He has 20 cows.
In fact, if he's into cows, I just read about a robot that's dedicated to sweep up the poop behind cows in dairy centers.
So, John, quick question on this while we're on this topic. So, because of the server side or the back-end computing is becoming so sophisticated, does it mean that the edge operating system, the operating system on mobile devices should not keep up with it as far as is it going to go slower on developing operating system for devices since they're just going to be like dummy kind of a display device because the computing power is happening on the...
Well, so I think there have been people who've argued that, but from what I've seen in the market, it's the opposite. There's a huge rush to increase the amount of computational power in the device, and that will continue because the more computational power you can put into the device, the higher fidelity graphics you can do, and so now it's becoming a cooperation. You try to do because, for example, if you can respond very quickly to a request on the device itself, then you don't have to connect. And for example, so probably where you're starting to see a lot of computing, and for example, people like running games on their device. Well, being able to run a sophisticated game is an indication that the device itself is pretty powerful. Has good rendering power. But yeah, so mostly the concentration is not so much in brute computing power, but in connectivity and in graphics. But so one of the things that kind of drives it, not only is there how to use the device, but the device market is extremely competitive, and so the manufacturers, in order to compete against one another, have a vested interest in trying to make their device the fastest and the most powerful device that they can sell at the right price point that you're interested in buying. And so there's a huge, all the manufacturers are constantly leapfrogging one another, trying to, to make their device the most sophisticated device that they can. So now we have, a device with cameras, with very sophisticated camera filters that are able to do all kinds of image manipulation right on the device. And so it's actually kind of a cooperative. You'll probably see some solutions that start on a device actually being migrated over to the data centers, and other solutions that required the data center before might be pushing some of their work down to the device because the device can handle it. And so it's constantly going to be sloshing back and forth. And as a consumer, it's wonderful. I mean, the power that you're going to be able to have in your pocket is phenomenal. It's really interesting. It's very exciting. And as a student, it's a huge explosion of the world. Probably one of the wonderful things about working in software is that the hunger for developers far outpaces the number of developers out there. I know that, like Microsoft, we probably have 10,000 openings at any one time. We're constantly looking for employees. I mean, basically, because software is this wonderful world where as you fix things, as you make things, you come up with new ideas of what else to make. And so then you need more people to help you make it. And it just grows and grows and grows and grows. And especially with, the number of devices is exploding faster than the number of humans growing. So yeah, you go into software, you'll have work for the rest of your life.
Yeah. John, just so you know, I would like to give more time to the centers to ask questions. So if we can wrap it up in 5 minutes, is that possible, or do you have?
Oh, I haven't. This is only halfway through the deck.
Okay. Yeah, keep going, I guess.
Okay. So I've talked a lot about the beginning. So the whole reason I talked about that was to give you, to kind of whet your appetite about why you should be interested in operating systems.
Okay.
And so what's an operating system? An operating system is the key piece of software that turns hardware into a platform for software. Because when you first turn on the device, it is simply an electrical device. It doesn't do anything really for you except consume electricity. And so the first thing that starts is the operating system. And the operating system is what creates this programming environment where your applications can now do wonderful things for the user, and you interact back and forth. So here's kind of a diagram of like the internals of an operating system. At the very bottom, you have the hardware. And probably the first thing that starts is the kernel. So the kernel is basically the brains of the operating system that directs file management, that directs memory management, that directs the hardware, that decides who gets to run. And the kernel works very closely with the file system. The file system is the part of the operating system that writes and reads from your hard drive and saves your files and opens your files. And then it works also with the networking, which basically treats the external world as though it was a huge file system, so you can read and write from other computers and bringing data back and forth and serve up websites and stuff. And then the window manager is what we often think of as the operating system. It's all the nice graphical interface and the buttons and things like that, and that's all being handled by the window manager. On top of that core is this application programming interface. And that's what your applications talk to. And so if you, as a developer, that's probably the first thing you learn is the programming interface for the environment. So, for example, there's a programming interface that's very specific to Windows. There's another one that's very specific to Mac, which is actually a Unix machine. And so there's two real huge flavors in the world. There's the Windows world, and then there's the Unix world. And they all have very similar commands that allow your application to say, I want a window, I want to open this file, I want to read and write. And so then your applications then live in what's called a user space, which is a protected environment that allows your applications to run, but it doesn't allow it to mess the operating system below. So the operating system keeps its own space, the kernel space, protected, and doesn't allow your operating, and so your application can only interact with the kernel space through the programming interface. The programming interface is basically this, not only provides the functionality you need to write your applications, but also is the layer of security that keeps applications from causing your computer to crash. And so your applications will do a system call. The system call will go through the interface, and that's where the kernel checks all the permissions, makes sure that your call is is correct. And when everything is correct, then the kernel will pass on your request to, for example, the file system or the drivers or something like that. They'll do the work for you and return the results back to your application. And a powerful operating system introduces something called virtual memory. And virtual memory is really is basically using the hardware and the kernel cooperate to create a bookkeeping system that makes it look like the computer has way more memory than it actually does. And it's sort of like what your bank does. Whenever you check out, you go to your bank and you ask what your balance is, they'll tell you, what your balance is, but they don't actually have that amount of cash in the bank itself. It's mostly bookkeeping. And so that's what the kernel is doing. The kernel is doing this bookkeeping behind the scenes that makes every application thinks it has plenty of memory to do everything it wants. So that makes it easy to program, but it also means that each application is protected from one another. Each one of these memory spaces is isolated from one another. So one person's application can't if one application makes an error, you can stop that application and it won't destroy the other applications. And so that's a huge part of what virtual memory brings to the system. And if you've used your PC and your Windows and stuff, sometimes you see an application crash and it's no problem. Well, the reason it's no problem is because that application is actually running in its own memory space, and all the other applications are protected from its errors.
Yeah, just to put it on the language. I just wanted to reference that the language that some of the audience might know is running Microsoft Word and the blue box that John had at the top is pretty much the operating system. Is that right? Like you have the application and then the operating system.
Yeah, and the reason, yeah, and so you might have on a 32 device, you actually have about 4 terabytes of memory space, and 4 gigabytes, and so part of that memory is divided up. Anyway, so it's mostly, we can burrow into the details later, but mostly what it is the kernel has its own memory space, and it protects it. It does everything it can to protect itself, because that's probably the most important part of the operating system, is for the kernel to protect all the other operating system functions. And then as an application starts up, the kernel creates a memory space for your application. So when you start Word, the kernel behind the background is creating a memory space for Word to run in. And so then Word runs, and when Word starts, it thinks it's the only application on the device. And it has plenty of memory and stuff like that. And behind the scenes, what it is every time Word asks for memory, the kernel goes off and finds a piece of real memory and hands it to Word and say, here, you can use this. And so it's all this bookkeeping going behind. And the advantage is that Word is now isolated from PowerPoint, is isolated from Internet Explorer, is isolated from whatever other application you're running. And this is a really powerful programming model. Of course, I mean, sometimes there's errors, and if something screws up in the device drivers, then your whole computer crashes, because unfortunately the kernel can't protect you from errors within the kernel, but it can protect you from errors between your applications. And so that's why the kernel works really hard to protect the kernel space and to isolate the applications from the kernel space, and to isolate the applications from each other. Okay, that makes sense?
Yep.
And then behind the scenes, this is actually a slide from a course I teach, so it's probably a little more detail than you want. But basically, what the idea here is that when you run all these different applications, the kernel has a scheduler that is flipping back and forth between all the applications, and it's doing it really quickly. It's not uncommon for the kernel to switch between applications almost 1,000 times a second. And it's that quick switching between the applications that gives the illusion of all the applications running simultaneously. So that's an important concept, is that on a computer, a PC, with a single processor, only one application is ever running at exactly at a particular instance. And the kernel is using a timer, so it's in the background, gives each application maybe 10 milliseconds to run. And after 10 milliseconds, it switches. So you get 10 milliseconds of Word, 10 milliseconds of PowerPoint, 10 milliseconds of Internet Explorer. And that is switching back and forth so fast that it appears to be smooth and seamless. It's like watching a movie. When you're watching a movie in a theater, they're actually showing you 24 separate pictures, one after a row. And because that's happening faster than your eye can see, it looks like it's a smooth, continuous motion. And that's the same thing that's happening on the computer. On the computer, we're switching back and forth between all the other applications at such a fast rate that you get the appearance of a smooth and continuous application, continuous system with all these things running simultaneously, when in fact only one is ever running at any one instance. Does that make sense?
Yeah.
Okay, so just to sum up, so basically, so now I'm getting towards the end here. So an operating system, the minimal features, has a lot to do with scheduling of tasks. And tasks on a small operating system are simple pieces of code. Think of them as very simple applications. On a more sophisticated, it's a full application or a thread within an application. And round robin means that each one's going to take a turn. So we switch around, and occasionally somebody has a higher priority and they get to run. And then there's a term called preemption. And what preemption is a operating system term that means you can interrupt something when you need to interrupt it. So the operating system can stop your application anytime it wants to do something that might be more important. And one of the things that's probably more important is exception handling. So basically, when you move your mouse, when you touch your keyboard, or when you touch a touch screen or something like that, you've created an interrupt that the kernel will then switch to the code that handles that. And that's why your mouse moves smoothly across the screen. because every time you wiggle your mouse, you're interrupting the operating system, and it's making sure it's updating the position of your mouse. And then there's a more sophisticated term called synchronization. And what that means simply is that the operating system gives you a way of coordinating between different tasks. You can pause things, you can wait for things, you can say, wake me up in 10 minutes. You know, all these are powerful things that enable your applications to work cooperatively with other applications, or to split your application up into what's called threads, and each thread can then work cooperatively, so you can do multiple pieces of work, and that's a very powerful programming environment. And then on a bigger operating system, then we have virtual memory, which we talked about, file system, networking, and graphical windows. And so that's basically, in a nutshell, the kinds of things you'll see in almost any operating system. So now to bring this all back together again. So here's that diagram of the Internet of Things. And one of the things I want to emphasize is that an operating system technology is one of the key technologies that makes all this work. Basically, all the edge devices are running operating systems, and the operating system creates this programming environment, and this is where your applications are going to work. And so if you understand how your operating system works, or at least the basics of how operating systems work, then you can write more powerful applications. You can leverage what's going on, and you can know why it works the way it does, and being able to really maximize your own personal power as a programmer. You can pull ahead, because I meet a lot of people that are professional programmers, and they really don't understand how their operating system works. And so when they need to tackle some of the more sophisticated problems, they don't understand how threads work, how to synchronize things, how to wait on stuff, and so that kind of limits them. But just with a basic understanding of operating system technologies, they can be considerably more powerful programmers. And being more powerful is how you sell yourself in the world, how you become more valuable to companies like Microsoft, Amazon, Google, etc., or even to yourself if you create your own startup. And so it's a great way for you to be part of this huge world, and really, the opportunities are endless. Nice. So I would say, this is a very exciting field. I mean, there's tons of work, tons of really neat opportunities, and the types of things that people are starting to do it's unbounded. It's only limited by your imagination. And so with that, I think we can go into questions if you like.
Yeah, thank you so much, John. If you can actually turn on your camera, if you click on that share button, it will go back to you, I think.
Oh, I see.
Yeah. There we go. Yeah. So last time with Chris, I went first with the questions, so I'll ask the other two centers if they have any questions. Isak, you have to unmute yourself if you have any questions.
Yes, we do, and I'm going to invite the person to come here because of the speakers, and I guess it's going to be easier if he comes in. Yeah, please.
Hi, everyone. Okay, it's my question is about the role of graphene. If you have heard of graphene, it's a new element, and it is talked all over the blogs and things on the internet that would be the next revolution about the technology. I don't know what's opinion. What is your opinion about that, and its role about size and capacity of processors? How to change those things, this element, graphene.
What is it called? Graphene?
Graphene. Yeah, so graphene basically it's a form of carbon that forms very thin sheets, and so it has a number of really interesting electrical characteristics. One, the material is very strong, and also it appears to be a semiconductor, and so the entire computing world is based off of electrically is based off of semiconductors, because semiconductors allow you to make transistors, which are basically electrically controlled switches. So you can use a little bit of current to control a lot of current. Graphene so far has is still really in the laboratories. There's a lot of hope that they will be able to make super low-cost transistors with them, but so far I haven't seen any applications. Right now, I would say almost 100% of the computing power is based on silicon, and we haven't seen. So graphene hasn't left the laboratories yet in terms of what you see in the real world. So there's a lot of potential there, a lot of potential both electrically, but also in terms of material science. For example, I live in Seattle, and Boeing is just up the road, and Boeing uses composites. So they're building airplanes out of fiberglass, and there is a movement to think that they believe that they will be able to make planes out of sheets of by gluing layers of graphene, and that will be even stronger and lighter. But still, it's still in the laboratories right now.
Nice.
Thank you.
John, if you can click on that share button one more time. I think it went back to sharing your screen.
Okay.
You just click it once, and it will take a little time until it. There we go. I think we're good. Okay. Any other questions from the center in Tirana? So there's two different centers, John. There's one in Albania and another country. And that's where the question came from. So, Isak, any other questions, or should we move on?
As a matter of fact, we have another question for John, which is related to the data centers. I mean, given the nowadays and developments, does it mean that in the near future, that's a prediction from the guy who addressed the question, whether a quarter of the world will be occupied by these data centers? I mean, what's going to be the size of the data centers? That's the key question, I guess.
So it's so some of the huge data centers are probably like 500,000 square feet. It's quite large. Probably if you've the size of several city blocks. But there's also a move to create smaller data centers and locate them within cities. So most of the really large data centers, where you build it is often controlled by how much land is available and how much power is available. And so, for example, we built a data center in Quincy because it's farmland, and also there's huge amounts of hydroelectrical power. But there's also a move to create small little micro data centers that are actually downtown close to people. So I know that we've built a little data center that's hidden downtown Hong Kong. There's some data center. There's a data center in one of the buildings downtown Seattle that people never know about, and it's actually the connection between the West Coast and Asia. And so that's the thing, is that, you know, basically companies like Microsoft and Google and Amazon, especially Microsoft and Google, we have a strong interest in bringing computing power to all parts of the world. For example, we're going to continue building data centers in Europe and keep on moving east and trying to build data centers, for example, close to Kosovo and close to Albania. But also, some parts of the world really are underserved. Africa's way underserved, and parts of Latin America are also need more data centers. And so, the team there's a group in the team I work with that basically their mission is to scout the world for locations to build data centers. Not only the huge data centers, but also these small micro data centers. To be able to store, so basically they can act like a cache to make sure that people can access their data really quickly, because you always want to take the data as close to the person that's using it. That way you get really smooth performance and stuff. And so there's a move to create these small micro data centers to serve all these different city populations. And so you'll probably see over time that almost every city in the world will have at least a small data center in it and serving the community there. And depending on how that the usage of that community grows, the data centers will grow along with it. I mean, it's starting to become it's starting to become one way of thinking about it. The same way, you know, first there was a big push to make sure everybody had water. and you created this big infrastructure for water, and then a big infrastructure for electricity. Now is a big push. Basically the next century is about making sure people have computational power coming out of their, in their house, the same as electricity and water. That's becoming almost a basic human need, I mean, because that makes humans more powerful, more healthy, more cooperative. For example, the internet allows us to teach classes across the world. Yeah?
Yeah. I guess when they discover another planet, they'll make this planet data center all over.
Yeah, yeah.
All right, so we're gonna pass it to the other center. Isak, I'm sorry.
Thank you. That's all from our side. I think that that's more than it was explanatory. For what we have addressed. I mean the questions that we had. So thank you very much.
Yep, thank you, Isak. And then now the ICK Innovation Center of Kosovo. You guys have any questions from your end? By the way, you'll have to unmute yourself if you have any questions.
No, Riva, we don't have questions. We just wanted to thank John for lecture. Great.
I have now a lot of questions here from my end, so I'm just going to read maybe a couple since we're running a little late. John, I'm going to skip the majority of them. It says, can I run games and programs that require Windows OS on TinyOS? So there's a lot of questions about TinyOS. Can you just...
Oh, no, TinyOS is really, really tiny. TinyOS is for small little devices like this. It's basically a learning platform. So I have here, let me show you the device I teach on.
Is that open source, so we can use it in any of the devices here? Or?
Yes, yeah. So I mean, that's the idea. So I'm working with another fellow, and we're writing a book on how TinyOS, because I have a strong belief that if you really want to master something, you should start with something really simple so that you can see every piece of it. In fact, TinyOS will turn a device like this, will make it, so here's a little screen, this is an ARM7 processor, and then these are all the other peripherals. And so we run TinyOS on here. There's a little joystick and little buttons. And the idea is to understand what the kernel is doing. And so basically TinyOS is simply the kernel that allows you to create multiple tasks and switch back and forth. So, and the idea is that it's every line of it is documented so that you understand what it's doing. Because if you understand a simple kernel, you'll understand all kernels. Because basically all kernels are basically designed the same way and all have the same requirements and basically do the same things. Mostly the difference between operating systems is the layers of services that are added on top of it. So TinyOS does not have a graphical system, so you can't do Windows. But on the other hand, you can turn this device into a very functional little machine and understand why it works and how it works.
Have you heard of Raspberry Pi, John?
Yeah, so Raspberry Pi is a small Linux machine.
Linux. So can we push TinyOS on Raspberry Pi, or that's a whole different kind of a device?
TinyOS should be able to work on Raspberry Pi. Definitely the software that comes on Raspberry Pi is way more powerful than TinyOS. So TinyOS is really, really an educational OS to understand how a kernel. I probably should have called it Tiny Kernel.
All right, last question and we're done. This is a little bit of an interesting question. Why Grand Theft Auto is not made for PC yet? It's a game that Microsoft, I guess, made it for what, Xbox? So the question is for you, since you work for Microsoft, do you have any information why have they not made it for PC?
Well, Grand Theft Auto runs on Xbox. However, it's not a Microsoft game. I believe it's what is it?
What is it?
TK or something like that.
Oh, I see. Yeah. So I guess the questioner, they didn't know that. So he just wanted to have it on PC.
So one of the games that is coming out is Titan, and also Microsoft works closely with Bungie, and Bungie's coming out with a new game called Destiny. And I believe these new games are going to leverage cloud computing graphical power, and so you'll see. So the idea is that these games will be even more graphical than you would think they should be, given the power of the Xbox itself. because they can go off and now use a huge farm of a huge rendering farm in the data center to render high definition scenes. And so as your characters play and evolve in the game, you'll get cutscenes that are actually designed specifically for your scenario in the game. And instead of having a generic cutscene that you might see in a regular game today, you'll have a cutscene that's your character, the way it's dressed, where it is, and everything like that, totally customized for your game. And so that will be very interesting to see the type of fidelity in the worlds that people will be able to animate in the future.
All right. Thank you so much, John. Enjoy the West Coast. And I know it's daytime for you, so you get the whole day in front of you. It's nighttime for us. But we really appreciate your time. This is all amazing. We're going to go over some of the things that you've talked about with the team here, and we'll keep you updated with what these hungry entrepreneurs are doing here. And if we have any questions, we'll try to set up a line of communication. So hopefully you can set up some time for us in the future.
Okay.
Thanks again,
Thanks
John.
everybody for listening in, and I hope I can whet your appetite. I've whetted your appetite and realized there's all kinds of wonderful things ahead, and you should definitely keep at it.
Now they're going to be interested about the device. Can you hear me?
Yes?
Yeah, I think we lost here. They're going to be interested about the device you had in your hand, so I have to explain to them about that TinyOS, how is that going to work. But thank you so much, John.
Oh, you're welcome.
All right, we'll go to the next one. I guess Isak and Elder Center, if you guys can stay online, I'll just talk about how we're going to move to the next session.
Yes, we're here. Just let us know. Give us the instructions.
Yeah, so I'm going to give you another link. This is a standalone recorded version, so this will we're going to have to get out of this Google Hangout, and then we'll send you another link, okay, on the same emails.
Please make sure that you send the invitation to Theodore and me, because we have two different computers using it.
Right, yep. Thank you, everyone. Again, we're going to end this Google Hangout session.
See you soon.
Yeah, thank you. Bye-bye, everyone.
Thank you.
Bye, John. Thanks.
Yeah. Take care.